The next question is what we're going to do with this experimental variogram. We obtained that by the experiment, we obtained that during the calculations. But what we're going to do with it? The thing is, we cannot simply use this experimental variogram because it's just a set of the points separated by a certain distance. But what we can do is we can approximate it with a certain function. And this function is called theoretical variogram. There are different types of functions that can be applied as a theoretical variogram. But in practice, we mostly use spherical, Gaussian, and exponential variograms. On the graph, on the picture, we can see the different shapes of these variograms. The main difference is like that. In case of the Gaussian function, on the very beginning, it's really flat, and then it starts changing dramatically. In case of the spherical and exponential variograms, they are changing dramatically from the very beginning. So what we're gonna do? We're gonna take our experimental variogram and then approximate it with one of our theoretical functions. Let's look at our experimental variogram. As you can see on the very beginning, it's nearly flat. The values are really small. Once you go further and increase your step to values of 5 or 6, it's increasing dramatically. So which of these three functions we're going to use as the approximate function for our experimental variogram? Most likely we're going to use Gaussian function. And let's see how it's going to look like as it's shown on our slide. What is important about our theoretical variogram? It should approximate as better as it's possible. It should approximate the initial experimental variogram. Now we're going to talk about the parameters of our experimental and theoretical variograms. There are a few settings that the interpreter have to work with during the geostatistics, during the work with the variograms. And these settings that you have to find are type of the variogram, range of the variogram, and the Nugget effect. Let's talk about these parameters. Type of the variogram. We already discussed that on the previous video. If we are talking about the Gaussian random function, on the very beginning it's flat and then it starts changing dramatically. While exponential and spherical start changing dramatically from the very beginning. That is the difference. The next setting is radius or the range of the variogram. You see, all theoretical variograms are coming to a certain plateau, to a certain asymptote. Why it's important? As we already discussed, if you take two wells on a distance separated by 20 kilometers or by 200 kilometers or by 2000 kilometers, it doesn't matter. They are going to be independent. That simply means that on a certain distance, our points became independent, and it's not changing with the change of the distance. That means that our variogram function should reach a certain threshold, a certain plateau, and then it's not changing. When our theoretical variogram reaches a certain plateau, we can find on this distance the value of the range or variogram radius. What does it mean? What does the range mean? Actually, range means the influence radius of the well. If your range is, let's say, 4 kilometers, that means inside the radius of 4 kilometers along the well, the values are nearly the same as in this well, or at least the values are dependent on the value of the well. Once you're outside of the range, the values are completely independent. The next thing is the Nugget effect. Let's look at our experimental variogram. You see the first point starts on a coordinate equal to 1, while theoretical variogram starts from the coordinate equal to 0. But why we did not calculate the experimental variogram on a distance of 0? The answer is easy. What does it mean? Distance is equal to 0. That means we're gonna compare the value of porosity with this well with the value of porosity in the same well. But what's going to be the difference between the values of porosity in a single well? The difference is going to be 0 because it's the same value. But actually, in a certain case, it can be not 0. It can be more than 0. How it can be more than 0? It can be more than 0 in case if we got some mistake in our data set. For example, we measure porosity in the well and it's equal to 10%. And then we measure it once again. And the newly measured porosity is equal to 11. That means we cannot 100% believe to our values of porosity. And that is turned out to became Nugget. The higher the Nugget, the more the mistake in our data set. Let's look at the example. We did calculate this experimental variogram and we did approximate our experimental variogram with the theoretical one. We see that our variation reached a certain plateau, and that happens on the range nearly equal to 5. So the variogram range in our case is 5. That means that the points on the distance more than 5 are independent in our data set. Nugget effect is equal to 0.